Hello, everybody, and welcome to Lesson 8.5. Today we're going to be talking about an idea called triangle proportionality. Now, proportionality is an idea that I think is very best summarized by just looking at something that's proportional rather than talking about what it means too much at first. So let's take a look at something. Um, Here, if you've ever seen Austin Powers um, movies, then you may have recognized these guys. This is Dr. Evil, and this is Mini-Me. Mini-Me is a smaller version of Dr. Evil. So these two are kind of supposed to be the same guy, where one of them is a smaller version of the other. If you look up, I looked up Dr. Evil height, and the thing that came up was if you define size as height, then to figure out the answer to the challenge question, how tall is Mini-Me, take Mini-Me's height of 0.81 meters and divide it by Dr. Evil's height of 1.73 meters, giving us a decimal of approximately 0.47. So Mini-Me is approximately 47/100ths the size of Dr. Evil. Okay, so this is their proportion, 0.47. It's very close to 0.5. If they have a proportion of 0.5, that would have been like 50 out of 100. And if you know how to reduce your fractions, you'd say 50 over 100 is the same as 1 over 2. So what that really means is that whatever um, whatever mini-me, whatever part of mini-me you measure, if you measure his arms, legs, his head, if you measure his head, Dr. Evil's head should be twice as big. If you measure Mini-Me's arm, Dr. Evil's arm should be twice as long. Okay, if you measure around his waist, Dr. Evil should be twice as big around the waist. Everything is proportional between these two guys. Everything on Dr. Evil is twice as big as everything on Mini-Me. Okay, so that's what proportional means. It means to have kind of a relationship between the sizes of things. And specifically, it means to have like a consistent relationship. So if you thought about, well, wouldn't it be kind of strange if these guys were unproportional? What would that look like? That could look like if they both had the same size head. So if Mini-Me's head was as big as Dr. Evil's, or if Dr. Evil's head was as small as Mini-Me, then you would no longer say these guys look very proportional. They're only proportional if there's a consistent, like constant relationship between the size everywhere on one person to the next one. Okay, so we're going to talk about that in the shape that we've been working on for a while in triangles. There's going to be a description here that I think seems a little bit wordy at first, but if we just kind of draw a picture of it, we can make sense of what they're saying without our eyes glazing over too much. It says that when a triangle contains a line that is parallel to one of its sides, okay, so a triangle contains a line that is parallel to one of its sides. Okay, that's what I just drew. This line is contained in our larger triangle, and this line is parallel to one of the sides, specifically the side on the bottom. When we do that, um, the two triangles formed can be proven similar using the angle-angle similarity postulate. That's something that we would have seen in a previous lesson. And because the triangles are similar, their sides are proportional. Okay, so their sides are proportional. Let's say that this one was we measured it and it was 1 unit. And maybe, or let's call this one 1. This one's 1 and this one's 2. Well, if it's going to be proportional, something that we could have like this little segment could be 6. And if it was 6, what do you think this segment should be? If you looked at that segment right here, what would be your prediction for what it should be? Well, if your prediction was 3, then you'd be correct. So our proportionality here would be 1 to 3. Okay, you could write it like that as a ratio like that, or you could say it like this as a fraction, 1 to 3, right? 1 over 3 is the same as 2 over 6. The relationship from this part to this part is the same as the relationship between these two. Okay, the relationship is that one is 3 times bigger than the other. Triangle proportionality theorem, the way that this gets stated is if a line is parallel to one side of a triangle and intersects the other two sides, which is what we have a line that is parallel to one of the sides of the triangle, and it intersects the other two sides of the triangle, then it divides the sides into segments of proportional lengths. So that's what we've seen here. So the original triangle would have had, we would have labeled it like 8 and 4. And when we made this parallel line in here, we divided those sides into proportional segments. So those two segments are proportional to one another. There's a 2 to 6 relationship here, there's a 1 to 3 relationship here, and that is the same proportion either way. Now, we don't have to put the line there. We could have put the line much lower, right? We could have put it like down here or something. So if we put it way down there, let's say, for example, instead of dividing that 8 up as 2 and 6, we divided it as, well, let's go the other way. Let's say like 1 and 7. Well, that would mean that this side over here needs to get divided up in the same way. Now that's going to be a little harder. We're going to need some fractions here. So what I would say is that we've broken it up in a way that 7/8 of it is here and 1/8 of it is there. So for example, what's 1/8 of 4? Well, 1/8 of 4 should be 4/8, right? 1/8 of 4 should be 4/8, which would be 1/2. And 7/8 of 4 should be 28/4, right? 7/8 of 4 is the same as saying that you're multiplying. So it'd be like 28, no, 7/8 of 4 would be 28/8, right? So sometimes we can do this in ways where the fractions aren't that pretty to look at. We could reduce that. We could get to 7/2 eventually. Okay, but the key concept here is that they are proportional. So if this is 1/2 and this is 7/2, well, obviously this piece is 7 times bigger than that piece, and this piece is 7 times bigger than this piece. So the particular proportion that we make isn't known until we kind of go through and test things out. But the idea that those segments will be proportional is what we call the triangle proportionality theorem. Okay. Now there's another theorem, and it's called the converse of the triangle proportionality theorem. Converse just means kind of like the reverse, more or less, like the opposite way of looking at things. So what this one's going to say is that if we start with this picture, if we start with a situation where we see proportional segments, so we say, okay, that is 3 times as small as this, and this one is 3 times as small as that, then what that means for us is that these two lines must be parallel. So the two theorems kind of say the same thing in opposite order. One of them says if you have those two parallel lines, it generates these proportional segments. And then the converse says if a line intersects two sides of a triangle and separates its sides into proportional corresponding segments, so if you draw that parallel line and it makes these proportional things, if you draw this line and you make these proportional segments, then that line must be parallel to the other side. They're really not saying different things at all. They're just saying it in one direction and in the other direction. Okay, so we'll use that idea in our next video in example number 1.